Thank you very much, Ashfaq, for accepting this invitation to come and speak to our students and to us. Dr. Ashfaq Ahmad is the director for the Experimental High Energy Physics Group at the National Center for Physics. He is the team lead for the Pakistani CMS collaboration. He will obviously tell us what CMS is. It's one of the two major experiments going on at CERN. He is actively involved in promotion of physics in general and particle physics in particular in Pakistan. And he's arranged many conferences and activities. He's a center of attention when it comes to things. Ashfaq, thank you very much. Please go ahead.
Thank you very much for the kind introduction. So let me start. So the plan was to talk about the phase 2 upgrade and the motivation behind the upgrade, why we want to do it. But in the last minute, I also included some introductory slides. So first I will go through them. So this is just to outline my talk, but as I said, I included some introductory slides, so they are not a part of the introduction. So I will straight go to my presentation. So what is a particle? So we are particle physicists, we search for particles. So if you can ask my colleague, Dr. Rizwan, what is a particle, he can explain it to you in terms of group theory. What is an elementary particle? So what we call it, that it's something which doesn't have any constituents. And the quantum field theory, normally we try to define in terms of elementary particle. It becomes very simple. If something we define in something which doesn't have any structure. So like a zero structure means a point like particle, and you can write equation for this for them a bit in a simple way. If there is a composite particle, then things become complicated. Most of the particles that we talk about, they are very short-lived. They decay either through strong interaction, through weak or electromagnetic interaction. So in particle physics, normally we talk about these three type of interaction or forces. Normally, the standard model of particle physics, as we know, it doesn't include gravity, so we don't talk too much about the gravity itself. And how the particle can be detected. So this I will talk about a little bit later, a bit more. And there are a lot of particles. Elementary of them, the elementary particle, they are very few. I will talk about them, but the composite particle, which have other constituents, there are so many. So like we can divide it into baryon or to meson. And baryons are those where there are three elementary particles inside. Particles are antiparticle. When I talk about particles, then normally I include antiparticle as well. So I don't too much switch to anti or I always talk about particle itself. And mesons are those which are having two particle or antiparticle inside it. So how we detect them? So the only way to detect detect a particle is that they should be interacting with some material, and when they interact with them, then they can produce kind of electrical signal because they deposit their energy. So by using those information, the energy deposition of those particles, we can measure the energy of those particles, or we can, for example, make a detector and put it inside the magnetic field. So over there, we can detect the position of particle where it passing, where the particle has gone through, and also we can reconstruct the path of that particle by using the position. So at the end, what we measure, it's either the property that we are measure for a particle. They are the position, direction, momentum. And normally we talk about high energy particles. So the mass of the rest mass of the particle, it doesn't matter too much, because when the particle, for example, if we talk about an electron, which is 50 giga electron volt, having energy of 50 giga electron volts, then we can safely ignore the mass of half MeV. And in that case, we don't differentiate between energy and momentum. So we either talk about energy or momentum, sometime one, sometime the other. So these properties are normally measured in tracking detector by putting it in a magnetic field, and the energies, they are measured what we call calorimeter. And once you have these information, then you can use simple particle physics and reconstruct the properties of the particle. For example, you can find out the spin, the masses of those particles, the invariant masses of those particles, lifetime, etc. So that is the way. And how we go about it. Once we switch on an experiment, then the first thing that we try to do, it is like using the known process, something that we understand very well. So we use those processes, those physics processes, and try to calibrate our detector fast. So for example, we reconstruct the diphoton mass. We can reconstruct, for example, dielectron mass. So if it's coming, for example, from Z boson, then we can reconstruct this peak very well, and it's very well understood. We can use it to calibrate our detector to see how the energy scale and the momentum scale of our detector look like. And once we validate it, then we go and measure something which is unknown. But before searching for new things, it takes quite some time, months and sometimes years, to really calibrate the detector, to align it, and to understand the energy or momentum scale of the detector. And once we do that, then we go for for example, for the measurement, for example, for precision measurement, for example, measuring the mass of W boson very, very precisely, or the measurement of the top quark mass very, very precisely, like what is shown in this plot. Or we can search, for example, for rare standard model decay processes. And why we are so much interested in that, because it also gives us, it's also like searching for new physics. If new physics exists in a way that it can change the decay rates of the standard model processes, we should be able to see it by measuring the cross section of the standard model processes. If, for example, they are more than what we expect from standard model process, then we can say that, okay, there is some mechanism which is either enhancing or reducing these processes. So this is like indirect search for new physics. Or we can search for something new, like, for example, we discovered Higgs boson in 2012 by Atlas and CMS experiment. Or we can search, for example, for supersymmetry or any other model which has been proposed beyond the standard model. Here you can see the limits which are there, the limits on the charge-union and neutralino masses. So what we do normally, we try to search for new physics, for example, for supersymmetry. If we have not seen anything, if we see something, some signal, then we try to quantify that signal by assigning what we call the significance of that result, like how big that signal is, how big that it stands on the top of the background. And there is a convention in particle physics, in general in physics, that if it's 5 sigma above the background, then we claim a discovery. And if we don't see a signal and we cannot assign, for example, a significance to it, then we put a limit on whatever property whatever we wanted to measure. And we say, okay, we are now with 95% confidence level, we can say that the mass is up to, let's say, 1 TeV. This particle, let's say the charge-ino and neutralino, the mass cannot be below 1 TeV. If they exist, they should be above 1 TeV. So how this when we talk about the LHC, then we are talking about the measurement of the proton. We are colliding protons, bunches of protons. So there are bunches of proton coming from one side and the other side, and this is like circulating in a 27-kilometer long accelerator in a circular form, and these are bunches of proton. So one bunch of proton, it like contain about 100 billion proton, and we are trying to collide them. There are a large number of protons, but still the probability of colliding them is very, very small. So people say like you are trying to collide two human hairs. One is one you sent from Geneva and the other from New York, and you are trying to collide them in the middle of Atlantic Ocean. So the probability for them is just like you are colliding these bunches of proton in LHC. So when you collide them, then the energy the collision is normally, it's not between two proton, but it's between the constituents of proton. If you go and ask a QCD expert, then the constituent of proton, it's not just simple three valence quark, but it's like a whole word. So there are C quarks, there are gluons, and they are exchanging in between. So you are basically colliding the constituent quark. And the fraction of energy which the quark take, it's much less than the actual energy of the proton. So the energy which is available for the production of new particle, it is actually less than what the energy of proton is. So this is a simulated event, how it would look like if two protons are colliding, and how the constituents of proton, they would interact with each other. So it's quite complex phenomena, but in every collision we make most of the collision, they are very soft collision, and in those soft collision normally new particle cannot be produced, so they are not that useful from the physics or new searches point of view. They could be useful for studying like minimum bias events, but they may not be useful in discovering new particle. So the actual production of new particle, the probability for them is quite low. One term that I will be using a little bit also when I talk about the high luminosity upgrade. So that is what we call luminosity. So what luminosity means? It's basically defined like this one. So the number of particle, I hope you see the cursor pointer. So the number of particles in the bunch coming from the left, bunches of proton, number of protons in a bunch coming from the right, the cross section for the collision of these two bunches, and this is the frequency at which the bunches are circulating. So for the LHC, they are 40 megahertz. That means that the two bunches, they are away from each other by 25 nanoseconds. If you convert frequency to the time, I think in the lengthwise it will be like 7 meters or so. So the luminosity, basically it's the number of interaction which are taking place per unit area per unit time. That is what we would call instantaneous luminosity, because we talk about per unit time, per second, for example, and per unit area. And if you want to get, and normally we are interested not only in instantaneous luminosity, but also the integrated luminosity, which basically determine the total number of interaction which took place in certain time. For example, I would be interested like how much interaction took place in the last 1 year. Then I would integrate it. Over time. I'm just trying to remove this. Okay. That will be what we call integrated luminosity. As I said, these are just some parameters of the collision. So I'll just skip this. So this is how the 27-kilometer accelerator look like, an aerial picture from the above. So this is like Geneva Lake. and the CMS experiment is a bit far away in a village in France. This is the Geneva airport, and this one is the LHCb experiment. And this is basically the main sun site near Geneva. This is called Mera. This is a small town inside Switzerland, but in the border with France. And the Atlas experiment is somewhere just here. And the Alice experiment is again inside France. So the experiment, they are basically underground, 100 meters below the surface of Earth. These big detectors, they are already inside these big pits. When I was a graduate student, I went for the first time to visit Atlas experiment. I was working on Atlas at that time. I basically spent 13 years of my life in Atlas, working on Atlas experiment, and now 9 years on CMS. So this pit was just under construction. Beside these experiments, there are now some more that have been added in the years, over the years as well. So this is how it looks like these are just Switzerland and France and these experiments and how they would look like, for example, under the surface of Earth, 100 meters down. Okay, so now I talk about what, I'll just focus on compact neon solenoid experiment. That is what we call CMS. So it's like 14,000 ton and the diameter is 15 meter. The overall length is like 29 meter. And it has many parts. The two general purpose detector, one is CMS, the other one is Atlas, and they are having the same structure. So normally we make it like onion shape. So you just, the different layers, basically they are different technologies and different detectors. They both are general purpose, Atlas and CMS, but they are complementary. So for each part, they are using their own complementary technology. So in one way, they are checking one another. So and this cross check is very important in physics. Otherwise, one experiment would see something and there will be no way to cross check the result. And normally in this case, if some interesting physics is seen by one experiment, most likely the other will see a similar thing. Sometimes it happened like a few years back, Atlas was seeing this high invariant mass, this diphoton mass, and then CMS was not able to see it, but the bump went away after a while, although a lot of papers were written on that bump. Okay, so then it has from inside out, the innermost part, the most sophisticated detector is what we call pixel detector. It's built from silicon pixel. And then it's surrounded by the silicon strip detector. So the innermost part, it's called tracker, and it's made from the silicon technology. And then if you go outward, then there is electromagnetic calorimeter for measuring the energy of electromagnetic objects, and then the hadronic calorimeter, and at the end there is a neon system. To tell you one thing more, for the pixel detector, there in the current CMS tracker, the pixel detector, the area is something like 1 square meter, and there are 69 million channels in the pixel. For the silicon strip detector, that is probably the largest silicon detector in high energy experiment, and the number of channels are like 9 million channels. Why I'm mentioning them, I will just coming to that point a bit later. And these detectors, they are basically placed in a 3.8 Tesla magnetic field. Okay, so why we need to upgrade the detector, and the reason is the following. You can see these are the different, for example, I talk about the innermost part, and this is the tracker part. So this is called This one is called tracker inner barrel, tracker inner barrel. So first layer, second layer, then tracker inner barrel, third, fourth layer, tracker outer barrel. So this is called first layer, second layer, third, fourth, and up to sixth layer. This make basically the barrel cylinders of the tracker, and they are surrounded by the disc. So you can count the number of discs on the positive side and on the negative side. And this type of geometry is important because you don't want to miss any particle. And also this is one thing, and the other thing is that you want to increase the number of layers, because the number of layers gave you the position in space, the position of particle in space, and you use that position to reconstruct the track of the particle and hence the momentum of the particle. So ideally, if I have a lot of money, then I would like to build a detector which should have many layers. But one has to reach to some compromise. So for that reason, you can see there are 6 outer barrel and 4, so 10 layers in the barrel, and similar coverage is provided in the end caps by putting discs as well. So what this blue and gray mean? Gray means the part of the detector which is working fine. Blue means the part of the detector which will be, for example, up to around 2025, that part of the detector would be damaged, and because of the radiation, it would not be able to function well. And that means that a lot of if it's not working well, then we would not be able to really to catch every single event. So in that case, our detector will not be efficient, and we will be missing our data. So we don't want to have a situation like that, and for that reason, we want to upgrade the detector. This is one of the reasons, but there are many others. So let me go a bit further. So why we want to improve it? Because we want to increase the physics potential of the machine and the experiment. And why we want to increase that? Because we want to search for a standard model process, and we want to search for beyond the standard model processes to see if something exists beyond the standard model. To do that, we need a lot of data, and to gather more statistic or more data, what we need, we have to increase the instantaneous luminosity to something like 7 times, I would say. So this is what we have right now, and you can multiply this by 7.5. So when we do that, then the plan is to accumulate data around 3,000 inverse femtobond. Till 2025, we would be able to accumulate something like about 500 inverse femtobond. But after upgrading the detector, we aim to accumulate to collect 6 times more data. And so once if you want to do that, then of course, we need to increase our instantaneous luminosity. Then that means a lot of radiation to the detector itself, and that means that for upgrading the detector, we have to use technology which should be radiation hard, which should withstand with the fluencies like 2 times 10 to the power 16 neutron equivalent per square centimeter. That means we have to do a lot of R&D to find out the option which can withstand high radiation environment. And just to tell you, the radiation environment at CMS, it's much more than the radiation that, for example, a satellite would accumulate in geosynchronous orbit for like 5 years. So increasing the luminosity means also that we are increasing pile-up. So the pile-up means that in a single bunch crossing, a lot of events, they are going to overlap. A lot of soft events, they are going to overlap with the interesting hard events. And currently, for example, we have around 50. The nominal one were 25. for the current LHC, but after upgrading it, it will increase to something like 200. So a lot of pile up. Now to cope with that situation, to cope with all these events which we are not so much interested in, but they are there, they would be there. We have to basically increase the granularity of the detector. And when I talked about 60 million channel in pixel and 9 million in strip, so that means that has to be increased in such a way that even with this pile up, yep.
Can you please just make sure if the slides are moving ahead, because we are at number 16. Is this the right one?
No, I'm on 18. Okay.
Yeah, that's what we thought, that perhaps they're not moving
okay.
ahead.
So you can just tell me. I'm sorry, but
yeah,
sometime yeah, something.
Yeah, sometime I think maybe you can stop sharing screen and start share screen again. Perhaps
so
that.
now you see motivation for high luminosity LHC.
No, we are still at 16.
आप अपनी sharing बंद करें एक मर्तबा, stop sharing करें, उसके बाद दोबारा से शुरू करें.
Okay.
Yeah, so that stops it. And वो मुझे बीच में लगा आपने कहा कि जी blue part of the detector जो है वो खराब होगा, and I couldn't see any blue on the figure. So
okay, so I am talking to myself now. You can you see now?
yeah,
Yes,
now
yes,
it's fine. Yeah.
Okay.
Can we just quickly see the previous slide जिसमें वो blue color नजर आ रहा होगा?
ये वाला, ये 17.
Yeah.
Okay.
Great. ठीक हो गया. चलिए जी, please go ahead.
कहानी
Thank you.
खत्म की. Okay. So is there a way that I can remove this somewhere? Okay, so I think it has to stay here somewhere. So I was basically talking about this. So the granularity has to be increased a lot. And also we don't want a lot of material inside our detector. So we have to, the idea is to reduce the material budget. And why we want to do that, if somebody asks me, I will explain later, but otherwise I will just go ahead. Also, we want to increase the to extend the tracker acceptance to up to an ETA of 4. So pseudo rapidity, I hope everybody knows that. And the tracking information, for the first time, why I said it's innovative. So for the first time, we are going to use the tracking information in trigger at level 1 trigger to trigger the event. So to decide whether the event is interesting or not. If it's interesting, then we have to keep it. Otherwise, we have to throw it away. So that would basically reduce the volume of data from the experiment, and we would be just keeping the events which are more useful for us, which are coming from hard collision. I'll not explain it further. So if you go to next slide, number 19, maybe I just pronounce it. So this is how the upgrade plan looked like. So we are somewhere around here and on the LS2. So I hope you can see my pointer.
We can see the pointer, yes.
Okay, thank you. So this one, the experiment is going to restart, and then it will be there for running for a few years, for a couple of years. And then in 2025, the LHC will be upgraded, the accelerator will be upgraded, and the experiments will be upgraded. And this is something that I explained why we want to upgrade it. So after that, it will then run up to 2040 and without any other stop. And it would be able to accumulate like 3,000 or 4,000 inverse femto, up to 4,000 inverse femto. So for CMS, this is maybe a bit redundant for people who are not too much into these experiments. So this is just the red includes those parts which are going to be replaced totally, and those parts where only electronics upgrade or partial replacements are going to take place. The green means new detector. So how this will change, for example, the physics potential of the LHC. So this is, for example, the coupling of the Yukawa coupling and the bosonic coupling of Higgs and as a function of particle masses. And this is how it looks like with the 8 TeV plus 7 TeV data. And this is how it would look like after we are able to accumulate 3000 inverse femtobarn at 14 TeV. That means after upgrading the accelerator and the experiment. And what will happen, that means that we would be able to reduce the statistical and the systematic uncertainty considerably. And why that would be important, as I mentioned before, that would also be very good. That could also help us to search for new physics indirectly as well. And of course, we will be searching for new physics directly by using the whole lot of data. And then why a lot of data is needed for searching for new physics? Because it might be that there might be some processes which are too rare, even for example in beyond the standard model theories, and we are not seeing them because we don't have enough data. So if we have a lot of data, then we can rule out that as well. This is just again another example. This is how the statistical and systematic uncertainty would look like with the 300 inverse femtobarn, which means something like the situation we have right now or we will have in a couple of years. And this is how this uncertainty would look like with the 3000 inverse femtobarn of data. This is if you were searching, for example, BSM Higgs. So there is, for example, this NMSSM basically predicts an exotic Higgs which can decay into two scalar pseudo-scalars, and then which can further decay in either to BB and tau or muons and taus. So over here you can see, for example, the ratio of the cross section of these Higgs to the ratio of cross section of the standard model Higgs, and as a function of the mass of these pseudo-scalar. So this is the situation, the ratio for 36 inverse femtobarn. These are projection basically. That means simulation, and 300 inverse femtobarn, and this is how it would look like with 3000 inverse femtobarn. So it's around 1. That means the sensitivity of searching for this exotic Higgs would be at the same level as we have the sensitivity for the standard model Higgs. That means if such a thing exists, we should be able to see it in 3000 inverse femtobarn, just like we have discovered the standard model Higgs. So same is the plot on this side. So the sensitivity is around 1. So if these, for example, exotic Higgs exist, then at this moment we may not be able to see it, probably because we don't have enough data, and that basically motivate us to go for high luminosity upgrade. So how the tracker will be upgraded? Just quickly. So as I mentioned before, the outer tracker as a whole, it was having, as I mentioned on the slide on CMS, it was having 9 million channels. But with the outer tracker means these are basically the layers of the detector in the barrel. On this scale, this is a scale in millimeters. So this tracker basically it's from 0 to 1,200 millimeter, that means a radius of 1.2 meter. Over these three layers, this corresponds to the outer tracker. We call them 2S module, and this is what we call pixel module. And this is a PS module, pixel plus strip module, and over here we will be placing pixel. So over here we will be placing something like a pixel which was first before 60 million channel, but now there will be 2 billion channel. And from here to here, before it was total 9 million channel, but now it will be 170 plus 11 plus 31. So it's like 213 million channels. So this is why I'm mentioning all these channels. That means the granularity of the detector has been increased substantially, which means that with the increased pileup, increased pileup means these 200 pileup events, we would be able to see to achieve the same precision as we have with the phase 1 or the current CMS detector. Other are more detailed, the number of modules, etc., and the number of the number of layers which a particle can pass when it passes through the detector, that can be seen here. So in this plot, the blue and the red, I hope you can see my pointer. I'm on slide number 25. So this is as a function of pseudo rapidity. So how these layers look like. This is the total number of layers by summing up 3 from the PS and 3 from the red, which are the 2S modules. So the total layers are always 6, except this transition region. And these 6 layers are essential for the level 1 trigger. So with the new detector, we are able to achieve the number of layers just from 6 layers from the outer tracker itself. And this is, if you know, the radiation length. So it's like the radiation length is a function of pseudo rapidity, which this shows basically the coverage of the current detector, and the different colors are basically the different parts of the detector. And on this side, this is what we call radiation length. So you can see it goes up to 1.5. So this shows the material which exists in the tracker when particle is passing through them. So this is how the detector look like to a passing particle. And this will become something like this. So the maximum is something like 0.8. And in fact, in over here in this region, it's much lower than what it was before. So the total amount of material has been reduced also substantially in the next upgrade. That means we will be now seeing particle losing their energy mostly in the active material that we are interested in, not in passive material that we have a lot in the tracker. So how we are what will be the impact of enhancing, for example, the acceptance. So these are, for example, Higgs decaying to 4 muon, and this is the PT distribution of the 4 muons coming from the decay of the Higgs, and these 4 muons can be, for example, arranged in terms of their PT, their transverse momentum. So there are some muons which are having transverse momentum with a mean around 50 GeV. That means they are high energy. The others are a bit low, and the third muon would be even lower. And the fourth one, you can see it's quite soft. So in the current experiment, we are cutting something like here or here. So we are basically losing these muons. But with the upgraded one, we are going to reduce the trigger threshold to 2 GeV. That means this will increase the acceptance of such events inside our detector. Similarly, the eta distribution, the coverage in eta, you can see over here. So before, the tracker was just between from minus 2.4 up to plus 2.4, but it has been, we are going to increase it even to 4. In this plot, the distribution has been shown for plus minus 3. So by including these events, you are really increasing the acceptance by something like 15%. So although we will have a lot of pile up, And in principle, resolution should go away, should become worse, but it's not so, because of the acceptance, the gain in acceptance that we will have with the upgraded detector. And this is the mass resolution, which is at the same level as the current one detector. So this is something that I want to explain a bit more now, and it's going more towards the hardware part. So how much time do I have? I think I still have 30 minutes or 40 minutes, right?
You wish. You wish.
Okay. So
You can take another 15 minutes.
15 minutes. Oh, I started late. Okay. Fine. So how the module looks like, the silicon module, it's basically two silicon sensor, these with strips engraved on it. These strips are called diode. And these two silicon sensor, they are having a space of 1.6 to 4 millimeter. And when a particle passes through it, then the module itself can decide whether the momentum of this particle is greater than 2 GeV or not. So this is a logic which has been embedded in the electronic chip, which is on the top of the sensor. It's a part of the module. So the module itself is acting like an independent entity, and it can sense the passing of these particle very quickly. I would say, let's say in 25 nanosecond. It's not exactly 25 nanosecond, but let's say so. So this type of logic has never been implemented before in any experiment. So we call them intelligent module or intelligent silicon module. And by doing this, basically it reduces a lot the data quite substantially. So it can throw away all the soft events which we don't need for the analysis, and it can keep all the interesting events that we would need later for analysis. So that is important, extremely important part of the upgrade. And how the logic works. So basically the electronic chip define a window. Window means the number of strips or diodes defined it. So it just detects, for example, something in the first layer, and then it tries to see whether in the second layer, the second silicon sensor, the particle is passing within the specified window or not. If it's passing in there, then it's about 2 GeV, otherwise below. So these information are used in level 1 trigger, and that basically reduce a lot of data, which is very good for us. So how this window is defined, it has been explained in this one, but I'll skip. How the silicon module looks like. So these are the sensor. This is the front-end hybrid with electronic chip. This is just a cartoon. I will show you the real one later. And this is a service hybrid, which basically provide power to power the module. And the window that I was talking about on the previous slide, that window that window requires that the two silicon sensor that must be aligned within 400 microradian. The angle between the two sensors must be below 400 microradian. And similarly, there are constraints for the pixel module. And also there are constraints for the X and the Y alignment of the two sensors. If you don't have that, then we would not be able to use it as a trigger. This is the performance, how the performance looks like. And this is the tracking efficiency. So the efficiency, the red one is for the upgraded one, and it's something like about 90%. This is a function of eta, pseudo rapidity, and you can see the momentum resolution. It's something like below 2%. And similarly, the impact parameter, the tracking, the track parameter resolution of the track parameter, it's around 10 micrometer. So having all the pile up, we are still able to see all the tracks coming from interesting events in the detector. And this is the efficiency of the stubs, or this window making, and it's closer to 99%. This is the electronics part. Maybe I skipped this as well. And the physics part, this is just some study of the TZQ we recently did, but I will skip them as well. So I'll come to the projects that we are doing at NCP for this upgrade. So we are basically have established a lab for the first time that is basically doing the qualification of silicon sensor at NCP, building silicon module and building also the ladders. So the project was funded by government of Pakistan, and we started that in 2018, and it was accepted end of 2017, and I was appointed as a project director in 2018. This is just a slide from the RPC, the detector that we built before for CMS. It's still there. The project can so basically I started the project and what had to be done. Three things. So when I started the project, I think the only one knowing a little bit about the silicon detector. That's why I wrote the project. Then, so the first thing was to train the manpower and to do the procurement, to establish the lab, and also to make technical progress, and all these three fronts. So this was the clean room, which was not that usable in 2018, and now I converted into this thing. This is how it exists. So in the clean room, we have the whole setup for building these sensitive silicon module with sensitive chips. This is the gluing machine. This is the robot that we locally built, because initially I wanted to buy this one, and this didn't arrive in time. So with an engineering student, we built this one, which worked very well, and it was quite cheap. This is the wire bonding machine, which can be used to wire bond using 25 micron wire. This is to remove the bubbles, a vacuum chamber. This is a probe station, MPI probe station, state of the art, that we purchased from a company in Taiwan. So this is the whole setup for sensor qualification. Maybe I don't go too much in detail until I get questions. This is just again, and I'm on slide number 46. Okay. This is how the silicon sensor looks like. That is a whole world. As I said before, the radiation hardness can be done in two ways: either searching for new material, but then the industrial limits come in, and then the other thing would be to redesign the existing technology. So the LHC, the whole all the experiment, they went for redesigning, and we found after the R&D that NNP silicon sensor, they are better and more radiation hard than P on N. These are just some plots how we validated our SQC setup. With the passage of time, it's completely functional. All the software has been developed locally, and this is how the measurements are made. And we have to report every week on Tuesday in the SUN meeting the progress that we are making in qualifying silicon sensor. This is a picture of the silicon sensor. About the module assembly, this is the glue mixer. So there we have a two-component glue, which has to be mixed in vacuum. And then you have to dispense. This is a glue gun, a dispenser, which has mechanical control. And then this was the robot that I was talking about that we have built locally. It worked very well, and really appreciated the hard work of the engineer who built it. He was from Multan, and my colleague Ahmad, he worked closely with him to build the robot. This is what we have, a robot from the company. And why we are using a robot? You cannot dispense this glue because the sensor with hand, because the sensor are too thin, like 300 micron, and the glue can spread here and there, which we don't want. Before building a silicon module, we have built 7 mechanical modules and validated them, presenting them at CERN meeting. This is the wire bonding setup. These are just the wire bond. You cannot normally see it with naked eyes, but you can see it under the microscope. And the engineer is well trained now, and has been able to bond already 3 modules. So for one module, there are like 4,200 bonds, which has to be made by using this machine. So the machine, once you load the libraries, it can work very nicely, but optimizing it is a lot difficult job. This is like sometimes the bonds are mixing, so you can see only under the microscope, and you have really to optimize the bond parameters to bond the silicon sensor and the hybrid. This is how we make the module, different step-ups, making a silicon module. This is this is a silicon sensor. After the Kapton tapes, we have to bond on the back using our machine. And these are the bonds which are, you can see, I hope you see my cursor, so you can see it under the microscope. Then you have to glue, to encapsulate it to protect the bond. Otherwise, the bond can be damaged very easily. So that we initially we did with this robot, our custom-made robot, and the minimum step size is 100 micron for our robot, and this is the speed. Speed can be controlled, and glue we use a syringe and air pressure and a motor to control the dispensing of the glue. This is how we build then the sandwich. And once you use the sandwich, as I mentioned before, you have to really verify that they are within specs, like within 400 microrate. And for that, we have developed a method that we call needle method, which has been validated with the Brown University in the US and also with the Aachen University in Germany. And after the validation, now we are successfully using it for the metrology of our modules. This is how the module metrology has been done using our probe station. Once the sandwich is made, metrology has been done, it's within spec, then we glue a hybrid. And at the end, you get the first silicon module. So this is something that we did in January. Then we made a functional module, and we obtained all the parameters within specs. This is a functional module, fully functional silicon and all the electronic chip. This is a bigger picture. The module has been bonded. You can see the bonds over here. These are the 8 electronic chips which are doing the intelligent work, receiving data from sensor and processing them and transferring them to the computer. This is how you test. You have a test setup. We have 2 test setup operational at NCP, and we are testing our module. The module have to be tested to see that all the wire bond that works fine. So you, as I said, 2000 on front, a bit more than 2032, 2032 on the back. And we do a lot of testing. And after testing, we then are able to validate the module functionally as well, geometrically by doing the metrology, and functionally by doing the by testing them in our setup system test setup. And then we present at CERN. Recently, we improved the geometrical jigs for obtaining the geometrical parameters further, and the metrology has been done by making another mechanical module. And something that we was achieving before 370 has been reduced to almost 1 microrate. And now this week we are making another functional module. Most of the job has been done already. In fact, the gluing and also the sandwiching and the bonding of the high voltage connector, that has been done as well. This is just the IV at different steps. So we have a module assembly line which is working properly. So these were the 2 projects. This one I will skip quickly. So another project that we are doing, which we are also responsible, the only group who is responsible to make all the aluminum carbon fiber ladders for the CMS experiment, and that's something that also we are doing at NCP. These are just the ladders, how it looks like. These are the component that we are fabricating with a local company in fact in Karachi, and the water jet cutting in fact done in Lahore, and with the company we are very good who can very nicely do all the water jet cutting. This was the first prototype that we have produced in 2019 and sent to CERN. And that was a proof of principle. A second prototype that has been built last year, these are the water jet cutting, as I mentioned. It's being used to make these windows, this special type of windows in this carbon fiber C profile. That cannot be done. That can be done in many different ways, but it's not acceptable. The only acceptable way is for a different reason is to do it through water jet cutting. This is our expert engineer, design engineer, Dr. Munir, and my colleague, Mr. Imdad. They are doing the assembly, and he basically did all the design and also expert at the assembly of making these ladders. And this was then tested at sun, and we were within plus minus 100 micron. The limit was 300 micron, and in spite of the fact that the constraint on us are too big, we have a lot of degrees of freedom, like 37 degrees of freedom, in contrast to the previous one at CMS, where there were 12 degrees of freedom. But it has to be built within 300 micron, and we achieved a precision on planarity of plus minus for 100 micron. It has been appreciated in this letter by Sun team to me, and documented in a paper which is submitted to the Sun document server. This is the third prototype that we are currently building, and after that we will be going for production next year. The complexity has increased a lot because of different design changes, but I think we are in line to do it properly. So this is just a summary of what I have discussed. And as Dr. Rizwan mentioned in the beginning, we are active in organizing school on LHC physics every year. A lot of people, students are participating in that, and workshop on tracking detector to increase awareness about silicon tracking detector in Pakistan. I think the field is not so famous in Pakistan, so we were trying to increase the awareness. So the next workshop is next month in October, and also organizing Asia Europe Pacific School on High Energy Physics for the benefit of the student. So that's all from my side. Thank you. I think.
Thank you very much, Ashfaq. Excellent talk, very informative, and it's very encouraging and very heartening to see the progress that you've made in developing these silicon trackers and these detectors to be used for the tracker. Some of the students have already asked questions, so we'll begin with those. And I think I will, instead of just reading out the questions, I'm just going to ask the students to just speak their questions themselves. Qazi, I'm giving you permission to ask the question. Please go ahead and ask the question.
Hello.
Yep. Yes. Go ahead, please.
Okay. So, sir, my question is that what was the main reason behind the diphoton resonance bump appearance? Why it was ruled out?
Because I mean, you see these fluctuations sometime coming in. In the Atlas experiment, I think if you remember, they were claiming that the significance of that is going to get bigger and bigger. And I think they went at some point to something like 3 or 3.5. But then the CMS on the other hand was not seeing any significant bump in that region. And later on they reanalyzed all the data, and they found that that was just a fluctuation. In the bigger data set, the bump was no more there. And for that reason, because there was nothing, sometimes things can fluctuate up and down. So it was not a significant bump. So for that reason, it was ruled out. So there could be noise going up and down. And for that is why in particle physics, we are using this 5 sigma criterion to claim a discovery. Every bump, everything that, for example, I talked about luminosity. So if you see something and you say, okay, the theory says that I am seeing, for example, I should be seeing 500 events. But actually, when you measure, for example, 550 or 600 events, let's say. Now, the question is whether you should claim something that you are seeing something which is coming from something beyond the standard model, or it's something like fluctuation. So to claim that, you have to go and study all the uncertainties and look to all your data. And if you see that you can control all your uncertainties and you understand it well, and still you are seeing something significant, then you can claim a discovery. Otherwise, for example, 100 events can just come because you are not understanding the luminosity very well. So you have to reduce really the uncertainty and luminosity. So the short answer is that there was nothing significant, and that's why it was ruled out.
Ashfaq, could you please elaborate a little bit on 5 sigma? I think it'll be interesting for the students to actually understand the meaning of 5 sigma.
Okay, I mean, if I want to claim something that I'm seeing something new physics or something new. Let's say I'm searching for Higgs boson, although Higgs boson has been discovered. But suppose you say that it has not been discovered yet. So you are looking into data, and for example, from the background, you look to first, how you will do it. You will just look to the background. You will try to understand all the background, and then you will look to the signal region. And in the signal region, at the end, you see some axis above the background. Now you want to decide whether this axis is. Sorry?
Notation.
Okay, so you have to make sure that whatever you are seeing, it's not coming just due to a fluctuation in the background. So 5 sigma means that the probability for background to fluctuate and give you signal is something like 1 event in 10 million. Okay, so that is something are 3 events in 10 million to be very exact. So that means that whatever you are seeing, you completely understood your background, and it's not really coming from the background. It's not coming from any fluctuation, but it's something significant, which is a real signal. So it's not coming from the fluctuation of background. The probability for 5 sigma means the probability for background to fluctuate is 3 in 10 million, 3 part in 10 million. You can even increase it. Some people talk about 7 sigma. So even you can say maybe the probability should be 1 in, I don't know how many billion.
Thank you, Ashfaq. Ahmad, could you please go ahead and ask your question?
जी सर, सर like beyond standard model हमारे पास ये 2-3 मॉडल आपने मेंशन किए थे, सूसी और एक्स्ट्रा डायमेंशन एंड लैप्टोकॉर. तो मैं जानना चाह रहा था कि इन ये मॉडल जो हैं ये डार्क मैटर सर्च में हमारे लिए हेल्प आउट करते हैं एक्सपेरिमेंटली, अगर हम इन्हें टेस्ट करना चाहें.
जो सुपर सिमेट्री है, ऑब्वियसली, यानी उसका जो सुपर सिमेट्रिक चेन का जो पार्टिकल है, जहाँ पे लाइट सुपर सिमेट्रिक पार्टिकल, इट्स वन ऑफ द कैंडिडेट फॉर द डार्क मैटर एज वेल. But that would be true if we could really discover supersymmetry, if the supersymmetry is really there. For the other than supersymmetry, there are many what we call Axion model, and some are saying these sterile neutrino, and I don't know, many candidates could be there for dark matter. But the thing is that we have not seen, I mean, supersymmetry could have some candidates if if it can be discovered, then it will also explain, for example, the dark matter as well. And it should have been discovered, for example, a long time ago, when I was a graduate student, long time ago, before the LHC started, like in 2014, or before that. Many people wrote the papers that just when the LHC is switched on, then the supersymmetry will pop up. Ridwan, I'm sorry, I'm not without any offense to you. So then, but then the LHC started, and we are now 13 years after the LHC, but supersymmetry has not popped up so far. So it should have been seen long time ago, but obviously some people say that Higgs boson was postulated in 60s and it has been discovered in 2012. So that could also be true. So we have to wait and see if the supersymmetry comes up, then maybe it has a well settled candidate for dark matter as well. So it would be able to explain dark matter as well. And the same also goes for other models as well. Extra dimension, अभी उसके लिए जैसे माइक्रोस्कोपिक ब्लैक होल्स है, उसके लिए भी हमने भी एनालिसिस किया, सर्च किया, लेकिन हमें मिला तो नहीं, तो उसका भी कोई एविडेंस अभी तक नहीं है. तो अगर चीज़ें आ जाती है तो फिर देखेंगे, मेरे ख्याल में उनमें से काफ़ी सारे हैं. But the truth is that dark matter is there. So it's our ignorance that हम उसे understand नहीं कर पा रहे हैं. But it's not necessarily that it could be supersymmetry, extra dimension. It could be something else जो हमने सोचा नहीं. हो सकता है बहुत simple चीज़ हो कोई जिसको हम मिस कर रहे हो. बाज़ औक़ात हम कहते हैं, वैसे चांद की जहन में बात आ गई, मैं कैपी कैसे हूँ, तो हम कहते हैं चांद उधर है. हो सकता है दूसरे डायरेक्शन में हो. तो
Yeah, so दूसरी direction में some people will be very happy if it's just a gravitation, if it's just a geometry effect.
So you do the indirect effects, we see it. So experimentally we know that it exists, but what it is made of, we don't know that. किस चीज़ से बना है ये नहीं पता. तो हो सकता है कोई और इसकी सिंपल एक्सप्लेनेशन हो. और ये मेरे ख्याल में, मैं तो खुद frankly speaking, मैं दो colleagues को I think about it, like for example a simple thing one can think about कि भाई जब Big Bang हुआ तो हम कहते हैं हर चीज़ उधर से आई, तो obviously dark matter भी उधर से आई. अब मैटर हमें 5% नजर आता है और हम उसको अंडरस्टैंड करते हैं. स्टैंडर्ड मॉडल इस 5% को तो डिस्क्राइब करता है, वेल एंड गुड. लेकिन जो 25% है वो कहाँ गया और वो क्या चीज़ है, तो वो हमारे आंखों से ओझल है. तो लेकिन ये कि आया तो ओरिजिन तो एक ही था, तो क्या चीज़ हुई कि वो मतलब ऐसे शक्ल में चला गया. अब एनर्जी से कोई पार्टिकल प्रोड्यूस हो, अभी जैसे पार्टिकल और एंटी पार्टिकल, अभी एंटी पार्टिकल इज विजिबल मैटर, it's the same as particle, so that has nothing to do with the dark matter. So similarly क्या चीज़ बनी होगी जो डार्क शक्ल में चली गई होगी. तो कोई चीज़ वायलेट हुई है और कोई प्रिंसिपल वायलेट हो के कोई चीज़ बनी है जिसको हम डार्क मैटर कहते हैं. तो एग्जिस्ट करती है, लेकिन क्या है ये नहीं पता. तो इन जब पता चल जाएगा तो ये भी पता चल जाएगा कि इनमें से कोई मॉडल इसको डिस्क्राइब करता है या नहीं.
Right, thank you. Asif, please go ahead and ask your question.
Excuse me, what LHC is looking for at the moment or up to the upgrade? I mean, what major breakthrough they are looking for now?
Obviously, जैसे पहले मैंने कहा कि बियॉन्ड द स्टैंडर्ड मॉडल फिजिक्स, जैसे मैंने मेंशन किया कि जैसे सुपर सिमेट्री के कुछ जो वर्जन है एनएमएस सिस्टम की बात की कि जो एग्जॉटिक हिग्स हैं हो सकता है कि मतलब वो एग्जिस्ट करता हो तो वो ये बताएगा अगर वो एग्जिस्ट करता हो कि सुपर सिमेट्री एग्जिस्ट करती है, और फिर काफ़ी सारी एक नई दुनिया शायद खुल जाए हमारे लिए। तो वी आर सर्चिंग टू सी, टू अंडरस्टैंड। हमें हमें ये तो पता है कि जो हमारी अंडरस्टैंडिंग है वो पूरे यूनिवर्स को डिस्क्राइब नहीं कर रही, इसमें तो कोई शक नहीं है, दूसरी राय भी नहीं। क्योंकि हम कहते हैं डार्क मैटर हम नहीं समझते, यूनिफिकेशन के लिए हमारे पास कोई ऐसी थ्योरी नहीं है कि सारे फोर्सेस को, ग्रेविटी को भी यूनिफाई कर लें, और एट्सेट्रा एट्सेट्रा। देयर आर मेनी प्रॉब्लम, जो ड्रॉबैक्स है स्टैंडर्ड मॉडल में वो तो एग्जिस्ट करते हैं और हमें पता है कि वो है, और इसी वजह से कुछ ना कुछ है। तो एट LHC वी आर आल्सो ट्राइंग टू मेजर the standard model processes precisely and to search for beyond the standard model. So the goal is still the same. और लेकिन हम समझते हैं कि ज़्यादा डेटा चाहिए। हो सकता है कि फॉर एग्जांपल सुपर सिमेट्री के जितनी अभी हम प्रिडिक्ट करते हैं कि पैरामीटर स्पेस इसकी ये वैल्यू होगी, इसकी ये वैल्यू होगी, तो इसी वजह से जो पार्टिकल स्पेक्ट्रम नीचे बनेगा वो लेट्स से 100 ऑफ GeV तक आ जाएगा। लेकिन आई मीन नेचर इज नेचर, इट्स नॉट, वी आर ट्राइंग टू स्क्रैच इट के नेचर में क्या है। लेकिन हो सकता है कि जो पार्टिकल्स है वो बहुत हैवी हो। सुपर सिमेट्री का मतलब क्या है कि कोई सिमेट्री है जो ब्रोकन है बहुत हाई स्केल पे। अब वो हाई स्केल कौन डिफाइन करेगा? शुरू में लोगों ने डिफाइन किया कि TeV से मैक्सिमम TeV स्केल पे या उससे नीचे, जिसका मतलब है कि अभी तक हमें नजर आने चाहिए थे, लेकिन जब नजर नहीं आया तो इसका मतलब इट्स ब्रोकन एट वेरी हाई स्केल। तो हाई स्केल के लिए फिर हमें ज़्यादा ऑब्वियसली एनर्जी भी चाहिए, लेकिन अगर एनर्जी नहीं बढ़ा सकते तो लुमिनोसिटी से बढ़ा सकते हैं। हो सकता है रेयर प्रोसेसेस हो जो हम मिस कर रहे हैं। तो द गोल इज स्टिल स्टैंडर्ड मॉडल प्रिसीजन फिजिक्स एंड बियॉन्ड द स्टैंडर्ड मॉडल सर्चेस।
Great, thank you very much. Is there any other question from the students? If there is, please raise your hand. So अशफाक, ये जो आपका है ये जो लैब में आप सिलिकॉन के ये डिटेक्टर्स के मॉड्यूल्स वगैरह बना रहे हैं, ये डेफिनेटली हाई लुमिनोसिटी के लिए अपग्रेड के लिए हैं। तो ये कब तक आपका प्रोजेक्ट खत्म होने का है? I mean, what's the time scale like?
अच्छा, ये obviously it's running from now till 2025, जो मैंने टाइम स्केल बताया। तो अगले यानी 3 साल में आप कह लें कि ये हमने बनाने ये चीज़ें, ये टाइम स्केल है। तो अभी प्लान यही है कि 2025 में LHC रोकेगा, इसको हम लार्ज शटडाउन 3 कहेंगे या फेज 2, ठीक है। तो इस ये जो 2.5 साल तकरीबन डिटेक्टर एक्सपेरिमेंट स्टॉप होगा, तो इसमें सारा जो हमने बनाया होगा अभी से लेके इन सालों में फिर वो इधर इंस्टॉल करेंगे। तो उसके लिए पूरा एक टाइम लाइन है। अभी हम R&D फेज से गुजर रहे हैं। प्री प्रोडक्शन मॉड्यूल का प्री प्रोडक्शन तकरीबन हमने वैलिडेशन और प्री प्रोडक्शन कंप्लीट करने को है, इसी तरह लेडर का कंप्लीट करने को है। तो अभी हम यहाँ लेके यानी सेकंड हाफ ऑफ अगले साल हम शुरू करेंगे और फिर अगले 2.5 साल में सारी चीज बनाएंगे।
अच्छा, इसमें जो आप वैलिडेशन कर रहे हैं, तो हाउ आर यू सिमुलेटिंग द एनवायरनमेंट ऑफ द कोलाइडर? आर यू वैलिडेटिंग इट इन दैट काइंड ऑफ एन एनवायरनमेंट या अभी वो नहीं हो रहा?
हम तो जो एक्सपेरिमेंट है, जो CMS है, उसका एनवायरनमेंट, क्योंकि ये लगेगा बेसिकली CMS का पार्ट बनेगा, CMS एक्सपेरिमेंट का। तो जो मशीन है वो तो डिफरेंट ग्रुप से जो LHC पे काम कर रहे हैं वो उसको अपग्रेड करेंगे, लेकिन जो हम कर रहे हैं वो तो अब उसका एनवायरनमेंट सिमुलेट करने का तरीका यही है कि जो अभी मैंने बताया जो मॉड्यूल हम अभी बना रहे हैं वो अभी नवंबर में डेजी में जर्मनी में टेस्ट बीम होगा। तो वही डोज जो LHC में रखने से 10 साल में जो डोज रेडिएशन डोज मिलेगा वो डोज उनको दिया जाएगा। तो बीम टेस्ट होगा। तो अभी जो हम बना रहे हैं तो अभी ये जाएगा नवंबर में बीम टेस्ट में शामिल होगा जो। और
Charlie, best of luck for the beam test, because once that is clear, then I guess you can go into full production.
right, exactly.
ठीक है. All right, Ashfaq, it's always a pleasure to have you around. It's always lovely to see you interact with the students. Or I don't see any other questions propping up. So thank you very much. Or we do hope to see you here on campus, here at LUMS, in the not so distant future.
इंशाल्लाह मैं खुश हूँगा, बड़ी खुशी होगी कि मैं उधर आ जाऊँ। और किसी का कोई क्वेश्चन हो मुझे कॉल भी कर सकते हैं, ईमेल भी कर सकते हैं। आई वुड लव टू आंसर अगर मैं
Yes, and Ashfaq's
मुझे
email is
पता हो।
available.
अदरवाइज मैं किसी से पूछ के आपको बताऊंगा अभी। बट
Right. Ashfaq's email is available on the NCP website, so you can contact him that way. And if you really must call him, I do have his number, so you can get it from me. Thank you very much, Ashfaq. Thank you.
Thank you very much.
बहुत शुक्रिया आपका.
Thank you, Ashfaq sir.
Allah Hafiz.
Allah Hafiz, thank you. So Rizwan, मैं off कर दूं?
जी, please go ahead.
चलो, thank you.